Hi and good evening and welcome to the Practical Welding Engineer. So tonight we're going to talk about arc energies in heat inputs, and this will be kind of a little bit of information ahead of a series of videos where we're going to start producing welding procedures. So I thought this would be a good one to kind of make sure we're all on the same page when it comes to this fairly critical measurement. So please remember to like and subscribe to see that as we come to it. I think they're going to be an interesting way of stepping through how to build documentation and where the pitfalls can be. So arc energy or heat input. So which one's which? Well, here we have our arc flashing away to itself. Which area is arc energy and which area is a heat input? And they're different between the specifications we use. So arc energy is the measurement of energy produced within the little blue flashing light that is our welding arc. And heat input is the value that is transmitted from the welding arc into our base material. So what are our calculations? Well, ASME 9 and AWS, they work on arc energy. So arc energy is amperage times voltage times time divided by our travel speed times 1000. The ISO specifications, so our qualification being 15614-1, work on heat input. And this is initially the same equation as arc energy, because we want to know how much is in the arc, but then we want to know how much is being transmitted over the arc into the weld material. So for that, we use a thermal efficiency value, or a K factor, which is applied to each welding process. So next step is we'll have a look at thermal efficiencies. So what are our thermal efficiencies? Well, for our given processes, and here I've just kind of put the most common processes you're likely to see within the industry. Here are our K factors, or our thermal efficiencies. Now you can see that these values change depending on which process we're using. We go from a 0.6 all the way up to a 1. So why are they the same for some processes and different from others? Well, if we look at submerged arc, here we have our weld, our arc producing our weld. Now the arc energy that's being produced in that welding arc is absolutely encased by a welding flux. So as far as the specs are concerned, 100% of the heat and the energy we're generating in that welding arc is making its way over into our weld metal. When we look at MIG-MAG, we have a welding arc, and here we're losing heat from the arc itself because we're no longer covered. But as we produce the weld, we're also losing heat through material which has been ejected from the weld pool, which isn't staying within our weld metal at the end. And then we take our GTAW. We have our arc producing our weld, but here we have no flux, so we lose material out from our lose heat out from our arc, but we're not losing material, and we have no spatter. But we're losing boatloads of heat from other sources, like our tungsten. Okay, so thermal efficiencies will change depending on the welding process we're using. So let's go through a worked example here just so we can at least do one equation together. So arc energy. So for this value, I have 120 amps times by 12 volts. I measured my welder for 60 seconds. And in that 60 seconds, he produced a weld which was 60 millimeters long. Okay, and he went for 60 millimeters in that minute, and we times that by 1,000. I get two fairly large numbers. So from the top line we get 86,400, and the bottom we have 60,000. Now, as a tip, your numbers should normally be fairly large. So if you get one of those numbers look, if you work out one and it says 2, your equation is wrong. Have a relook at it. So for this setup, we have an arc energy of 1.44 kilojoules. And because I'm sitting here in England, I'm working out in millimeters. You may have it in inches. It doesn't matter. The equations is the same. Then to work out my heat input, because heat input initially starts the same as my arc energy, we have the same value of 1.44 kilojoules. But now I'm going to times it by my thermal efficiency. So for this example, I've chosen TIG welding. So I times that value by 0.6. So that gives me heat input of 0.86 kilojoules a millimeter. So 40% lower, because I'm losing heat and energy in all sorts of areas within my TIG process. So what happens if we start to change our heat input or our arc energy? Why can I not just say, well, I've qualified a weld procedure and now I'm just going to throw up my amps so I can get as much material as possible, get that weld done as quickly as possible, and we're all happy, right? Well, as our heat input increases, two big things are going to happen with our hardness and toughness values. They're going to fall away. Yeah. Now, toughness value is your ability to withstand impact, and your hardness is the ability of the material to withstand indentation. So has the designer of your fabrication accounted for those being critical? If so, we don't want a runaway value within our heat inputs. Those drops in hardness and toughness values are being driven by an increase in our grain structure size. So low heat inputs produce a grain structure which tends to be very small, and on the harder side to heat inputs which are very high, we have large grain structures and therefore lower hardness values and toughness. Our weld bead is going to change as well. So from low heat inputs, we can expect to see a smaller, shallower weld, all the way through to a weld which may be very deep and very narrow. Now, welding process such as submerged arc welding quite naturally produce welds such as that. And that can cause us problems too, because now we start to see welds with large grain structure, columnar grain growth, which will lead to solidification cracking. So once we understand how to measure our heat inputs, we should also start to try and understand what a designer is expecting from the performance of that weld and why we have to control it. Now, the biggest effect on heat input can be travel speed. Okay, now if I put down a string bead at a given amperage and voltage and measure that, I'll get a given heat input. Now, if I then get the welder to start to weave or walk the cup along the weld with the same amperage and voltage, what do you think's happened to my heat input, my equivalent heat input between these two welds? Well, of course, a shorter run-out length, if we're talking about MMA, or a generally shorter weld bead, will put a higher heat input into the same area of material. So if you find that your welders are either too low on the heat inputs or too high, of course the easiest thing to do is get them to either speed up or slow down. That will have a drastic effect on the value that you start to measure, more than changing a few amps or a half a volt will get you. So in today's video, we've gone over where our heat input and arc energy is different, how we measure the two, how we can affect the heat input through a very small change in travel speed, and also the effect of our heat input on our overall material properties. So with that, I'd like to thank you for joining me tonight for tonight's video, and remember to look after yourselves and look after each other, and I'll see you all next time.